Module 7, Vectors. Specifically, Lesson 22, Vector Properties and Operations. In this lesson, we will dive into the properties of vectors, and we are going to see two operations, one involving a combination of two vectors, and one involving a vector and another value. A vector, overall, is a quantity that is represented using multiple values. Geometrically, it is represented as a directed line segment, where the magnitude of the vector is taken to be the length of the segment, and the direction is made clear with use of an arrowhead at one endpoint of that segment. We can see a couple vectors in the image on the right side as demonstrations of this. The vector has an initial point where it begins, and a terminal point, indicated by an arrowhead where it ends. When represented on a rectangular plane, a vector v can be represented in component form, or sometimes rectangular form. V equals a comma b, where the first number a represents the horizontal x component of v, and the number b represents the vertical y component of v. I will also say that sometimes you see vectors demonstrated with a little arrow over the variable to represent that vector, for example, v with an arrow over it. And sometimes you see the vector represented instead with a boldface. For example, in the image on the right side here, we see the letter v is bolded. That represents it as a vector. For examples where you will see work done with vectors, it is more commonly done where vectors have an arrow over it, as it is a little bit hard to write a bolded character with your pencil. The picture to the right demonstrates the vector v equals 3, 4. And note that we say here that it only represents that one vector, even though we see two of them listed here. That is because the two vectors on the side here are the same vector, actually. They have the exact same magnitude, and they have the exact same direction. They are both going to the right 3 and up 4. Since they are doing the same operation, they are the same vector, but they're just positioned in different places. This is going to be a very important aspect of vectors, that you can maneuver them around. However, it is very common that you structure vectors initially, at least, to be set at the origin. So for example, we would very commonly write the vector v starting at the origin, going to the right 3 and up 4. So something like this. But depending on the situation, particularly if we consider a vector like a force, we can position the vector in a more appropriate place that can help with a lot of our calculations. So know that a vector is a little bit more malleable. It doesn't have to end at the point a comma b. It just needs to go a horizontal distance of a and a vertical distance of b. Let's talk about some operations we can do with vectors. Here we will talk about two specific operations that you can do with vectors: vector addition and scalar multiplication. Suppose v is a vector with components v1 and v2, and w is a vector with components w1 and w2. The vector v plus w is defined by the two initial components v1 and w1 added, and also v2 and w2 added together. This essentially means that if you do want to add two vectors together, all you need to do is add the according components. Add the first components together and add the second components together. Essentially what this is doing is it is combining the overall horizontal movement as our first component and the overall vertical movement as the second component. We also have, if k is a real number and v is again the vector v1 and v2, the vector kv is defined by k times the components v1 and v2, which is essentially just going to distribute the real number k to each component, giving you the new first component of kv1 and the new second component of kv2. Essentially, this just means that you are scaling a vector by some amount. You are either extending it or you are contracting it. If k is a number larger than 1, then you are essentially taking this vector and elongating it. You're stretching it out. Whereas if k is a fraction, for example, that would take it to be a portion of what the original vector was. So you're going to shorten its length. However, that only really influences the length of it, the magnitude of the vector, unless the value of k is a negative, in which case the direction would now go in the opposite direction. You can combine the concepts of vector addition and scalar multiplication to also consider what, say, for example, vector subtraction would look like. Vector subtraction would be, as you would expect from vector addition, just what happens when you subtract the associated components. So, for example, if I wanted to do v minus w, I would take the first component of v minus the first component for w, and then the second component for v minus the second component for w. But concepts like this is established with a combination of the vector addition and scalar multiplication, where you consider -1 as a scalar on the vector of w. There are more properties that you can establish with concepts of the addition of vectors and the scalar multiplication of vectors. However, we are going to leave it as it is right now, but I will say one more thing about scalar multiplication. Note that when we write scalar multiplication, we write this as k times v, or whatever number you have times whatever vector you're working with. But I will not use any other symbol to represent multiplication. For example, I will not use a dot to represent the multiplication of these. This is not the same thing. And it's also not the same thing as if I were to use a cross to represent multiplication. When working with vectors, those symbols actually mean different types of multiplication, different than scalar. So, do not use these symbols to represent scalar multiplication. Simply use adjacency between the scalar and the vector itself.